All right, welcome everyone. It's Friday night time for another random coding challenge. We'll try to crack another problem under 40 minutes. This stream is for entertainment purposes only. And let's see what we've got today and can we solve it? Pick one. Thanks God, finally on Friday night I've got an easy problem. It would be super fun if I won't be able to solve it. Though. Anywho, let's just, I don't know, try to solve it fast, and then maybe if we have extra time, you'll see maybe we can code it in some weird language. Just saying, given the array nums, for each nums I find out how many numbers in the array are smaller than it. That is, for each nums I, you have to count the number of valid j's such that, first of all, they're not equal, and two, they are lower. Well, I mean, you know what it is, right? It means sorting. We just sort and log n time and whatever order we want, and then the position of this element will be basically how many elements minus those elements that we don't count. All right. 4113. There's nothing, there's nothing, there's nothing, there's nothing, there's nothing. Nums length 500, nums I 100. Okay. So numbers are always positive. They can be zero. It's great. Okay, so let's see on the whiteboard if there is something we're missing. So let's start with this example, right? Yeah, easy problem technically, you don't need whiteboard, but still, maybe I'm missing something here, right? So this is array we will be given at the beginning. So one, let's do out here. And whatever, sort. So once we sort, we will have this array, right? 1, 2, 2, 3, and 8. So now, I mean, it doesn't really matter which order we want, but now the position of the element basically tells me it tells me two things. So we start with linear time here, right? So this is n log n2 in ON traverse something, right? Traverse sorted array. right? So, all right. So for 1, it's 0, obviously, is the smallest one. For 2, we say 1. Why? So here is 2a part comes in. We track prior element plus prior plus prior position, right? So update prior element to be update prior element if and only if it's lower than current value. So if it's equal, we don't do anything, right? And 2c that num elements or whatever it is, num elements smaller, num elements smaller is this what? Prior no, it's this, right? So we say element strictly higher than prior element. If so, then element position, otherwise prior element position. That's it. So the total complexity will be or n log n. So this is the fastest you can get here. That's why it's an easy. Although to be honest, I have no idea how to sort and track the indexes of the sorted array unless you do pairs or something like that and then sort based on the first pair. Let's Google, right? We don't need to know the syntaxes or everything. CPP quick sort. We do quick because we don't care about relative positions of the elements. We just need to sort them to quick sort with indexes. So how do we do this? All right, let's just whatever. CPP sort, we don't need quick, it will tell us sorting can keep track of indexes. So that's what basically we want. Certify B. Using C++ lambdas. Here we go. Stable sort. All right, let's just copy paste this stuff. We don't need also a specific type definition. It will be in, so we're fine here. All right, that's how everything can be solved. Just Google it. If you have a problem, just Google it, and that's it. So we return vector of what? Of int. I prefer to have ref like this. Then we say initialize the original. We don't care about stable. We can just use sort. For us, doesn't really matter. In V, that's it. Right. Initialize something, whatever, begin, dx, v size, let's begin. So we don't need, we can just v size. It's basically index location. So it's basically the vector of from 0 to whatever size -1. Okay, I got it. So yeah, it should be straightforward. So we can just a little bit reduce space here. That's it. So what do we do is we say, basically we do sort, right? First sort, and we say idx, right? That's what it is equal to sort indices nums. Once we have it, traverse in O1. So by the way, we'll check the order at which it's sorted, but I would imagine that CPP sort order. So what's the default one? My int something vector, my vector. So by default it will sort it. All right, I see. So that's it. Int pref element. We can start with 0, whatever. If it's the smallest, the smallest. And int pref position is also, you can say 0. So what do we do is this, right? So we go through every index. So for int I equals 0, I less than idx size or num size, doesn't matter. I plus plus. So now we say update. So if if nums of idxi, okay, not the best one, but okay, now if nums of idx1, so the element value, right, is strictly greater. It's not just greater or equal, but strictly greater than previous element, then we say what? Then we say previous element equals to this. And previous position equals to idxi. Or no, the position in this one, so to I. All right. And then we say that nums of this thing equals to previous position. It's not just previous position, we can just say num elements and whatever. Who cares? So that's it. Looks like. And of course I forgot to switch it, but again, whatever. So that's what we've copied from Stack Overflow, this function. All right, so we can say sort indexes. So it doesn't look like we copied it. Okay, nums from 0 to 100 and minimum length is from 2, so we don't need to worry about it. It should always work. Okay. It's just okay. It's Friday, so let's not waste the time. Let's just debug it quickly. A year or two in development and all right, seems it works. Whoa! Oh my goodness, runtime 0 milliseconds, faster than 100% of C++ online submission for how many numbers are smaller than the current number. Done it. And for memory, we actually can run it multiple times. But I would imagine, so the index is vector size t. We know it's small, so but okay, I think it's okay. So this one takes a lot of memory potentially. Those are two tiny numbers. All right, I just submit a few more times. Now it's at 8 milliseconds. So we want 0 and a bit better memory, hopefully. Let's see if we can get everything. Okay, now let's see if we can get this thing. Let's see if we can get this thing and this thing, and this will be our final numbers, I would imagine. No. Oh, did I? 4 milliseconds. Still not as great as 0 milliseconds. I want 0 milliseconds. Oh no. Eight milliseconds. Are you kidding me? Now it's stable 10.2, so it's optimized something, but the time is not as optimized as the first one. All right, just let's see. I'm already okay with 4 milliseconds. Jesus Christ. Come on, give me 0. Why you can't give me 0? Okay, 4 miles in memory is worse. Oh my goodness, no. So the minimum I agree is 4 milliseconds and 10.2. So the best one is 0 and 10.2. or 0 and 10.3 is also acceptable now. Okay, 0 and 10.3, I take it. All right, let's switch to whiteboard. And today we hit a good number on time complexity because we solved it in near linear time, although most people, I guess, solved it in quadratic time. So we did good. And memory wasn't the best one. I would imagine if I just convert. So we know, let's see, we know that this thing, right, is what? Is 500. So technically we don't need, do we have just 1 byte? I wonder. Yeah, we do have it. So let's try actually this thing. Um, let's see how much we can save in terms of memory. We still have plenty of time, it's just 20 minutes. So by jumping to space complexity, I decided to just switch to from size t to unsigned integer 8 because we have 500 elements, which means unsigned is all 8 bytes, sort of bits can be used, right? So 2 to the power of 8, it's 255. Ouch. So we can just reduce it like 8 times. So okay, let's reduce it 4 times and go with 2 bytes. This definitely is enough to cover our case. I'm not sure if this thing is still going to work, but I hope so. Should be. So we do this, we return this, and then we use this here. All right. I can also use this thing here. And previous element, we also know that it's up to. So here's another interesting thing. This guy is actually, it won't save us much. It's like 1-2 bytes. But this guy is actually is 8 is sufficient because it's from 0 to 100. So we should be, it should be enough to cover with unsigned 8. All right, but I would imagine now we need, all right, now we would need, when we talk about previous elements, use static cost to whatever we do, and static cost will be what? 8. And previous position should be static. It doesn't because I is already unsigned integer 16, and we can always cast to higher integers. So okay, and nums we don't allocate it, we just redo it. Okay, let's see if it did anything like anything at all. Yes, we shaved another 0.1 megabyte. Oh, Jesus. All right, so can we get 10.1 and 0 in 1? Now it's 10.2. At least 10.2 and 0. So we can get extra points. Whoa! 4 milliseconds and 10 megabytes. How is that? Um, all right, we know that it can be done in 0 milliseconds. Should I just use the best memory here? Okay, I will use the best memory here. Heck not. Why not? Because it's Friday. So I would imagine that this is 0 milliseconds, so it's 100 scores here, and this is 10 megabytes, which means 83, score of 83. So I'll put 83 here. Oops. 83, and the total is 183 out of 200. But again, I'm not sure if everything is legal here, so let's be a little bit cautious. All right. See you either Saturday or Sunday. Have no idea when I want to take a rest, but whatever. See you.